notification. All right. So Marty Groman, E2 Tech here, and I have the honor and pleasure of serving as executive director of this fine organization. Nice to have a previous executive director and founder, John Furland, on. We got a nice number of companies to tell you about here. We just had a membership and marketing committee meeting this morning, and right around 325 member companies. So we've been growing. We always appreciate you recommending us. Being a member of E2 Tech can be, you know, a sort of a get what you give type of thing. And sometimes the benefits are not always that immediate. So the people that convene and promote this organization are greatly appreciated. And being a connector is what we seek to do. Right now, I'm working with a wood products manufacturer in Piscataquis County to help them develop some connections with MTI, and that's been good. These events are always free for students. These E2 Tech Connects events are free for members, and they're only 10 for non-members. So these are meant to be a way to convene around a conversation, maybe like you might have in the hallway at an in-person event, and just dig into some ideas. So we'll have a presentation and then a discussion. We've been doing a lot with promoting diversity within our sector, and we've had some good luck. Recently helped an engineer find a position, an electromechanical engineer, originally from Burundi. I've been working with this gentleman for 2.5 years now, so through schooling, through certification, through you name it, and nice to see him land on his feet. We're actually doing, and some of you are coming to, I think, an MTI event tonight. This is expressly for members of MTI's targeted technology boards, and we're really proud of our work with MTI and that they choose to work with us. Fine organization. If you've got that great new idea, you listen to Don's presentation and you say, oh my gosh, I'm going to invent a device and I need to do a market study, reach out to us and we'll get you going with MTI. Our job is to promote the growth of innovation in this sector. It doesn't have to be a startup. It can be a new idea for your existing company. As long as it's an innovation, MTI is ready to partner with you. And these companies partner with us, so please support them throughout the year. They make a $2,500 commitment each year to promote this sector. And we've been able to do that at E2 Tech. And these companies are the partners that help make it possible. I always like to kind of linger on this slide too, because this is the $1,000 level support. I'll highlight Crederi here, which is a new, just joined as a sustaining partner, and we're really appreciative of them. And also you see on the lower right, very new Royal River heat pumps. So please, any of these companies here, and I have, of course, John from ORPC. And John, we got to fix your logo. I know there's a new logo. These companies support us all year round, and if you'd like to become a sustaining partner with your company, we would love that too. And all of our forums all year long are promoted by TRC and BHB, these fine companies. And if you would like a print subscription for free to Main Biz, shoot me a note, Marty at e2tech.org. Because of our partnership with Main Biz, you can get a free print subscription, and it's actually kind of nice. They come out quick.
Scheduled on Monday, August 1st.
Hold on here. I'm quick with the mute button usually. All right, and just 1 second. Okay, so I have one more slide to tell you about, and then I will introduce Don. So this is a great event that we've got set up that I think you'll be interested in. This is 2 weeks from I guess 2 weeks from tomorrow. Anyway, the 26th, 2 weeks from yesterday. Thank you. California just opened up an offshore wind lease. We have a member company, Burns and McDonnell, that has substantial operations in California. They were involved in participating in this lease and advising and so forth. They're going to tell us how it went. And offshore wind is obviously a major opportunity for Maine. They're going to make some comparisons and tell us what they think. So you can unmute at any point. Please do stay on mute while Don is speaking. we are recording. You can send me a chat, or you can just use the chat. I'll just put in a chat that says hello, so we can use it. Just use it as much as you like, and or I'll probably just call on you, because that's a more participatory way to do it when it's time to ask questions. And with that, pleased to have Don Parent with us today. It's funny, Don and I were talking. He's been a longtime E2 Tech member. Thanks for all your support over the years, Don. And he recently renewed, and I was looking up, what does Don's company do? And I thought, geez, that's really interesting. I wonder if he'd give us a talk on the work that he does, and with a little back and forth and not putting up too much resistance, Don agreed and has worked up a couple of examples of the work that he does. So I think you're going to be really interested. So with that, I'll take my slides down. And Don, you can pop yours up, and
right.
Bryant and I are here to support you in any way that you need.
Let's see here. Thanks, Marty. I got to share my screen. Let me make sure I'm doing that right.
It looks great.
How's that look? That's okay? Good.
Oh, yeah.
Excellent. Let me go to the beginning here. And let me turn on the cursor.
Oh yeah, the fancy cursor.
Yeah.
I like it.
And I think we're in business. So
yeah.
Hello, everybody. Thanks for joining us. I see some familiar faces out there. That's great. I like seeing that. That's great. Anyway, when Marty asked me to do this, I thought that sounds pretty good. I could do that. And in particular, though, the goal was to actually present on things that are really related to energy or energy-associated incidences. And two came to mind right away. I've been doing this type of work for a number of years. I've been consulting for maybe about 20 years now. And that's ranged from multiple various areas. I used to be in manufacturing of high-tech equipment for CDs and things like that. But now that I've been consulting, I've been working on product development. I finished a project recently for the Army, for example. And also, I have been consulting with attorneys on patents and intellectual property litigation. But in particular, and what we're here to talk about today is fires and explosions and failure analysis as it relates to fires and explosions. And one of the things that I've learned is that a lot of fires and explosions happen for many, many reasons. But one of the very common reasons is failures of various types. So it's a great place to operate from a forensics perspective. And so if you look up the definition of forensic engineering, there's a lengthy definition. It's paragraph long, but we don't need to read it. It's basically this: the forensic engineering is the art of figuring out what happened and why. That's it. It's that simple. And but obviously in practice, it isn't that simple, but as a definition, that's pretty straightforward. There are two events that occurred that are notable and significant. One is a freezer storage warehouse fire that occurred in New Jersey a number of years ago. And the other one is a duplex home natural gas explosion that occurred in Lawrence, Massachusetts. So first we'll talk about the freezer storage incident. This turned out into what looks to be probably the largest solar associated fire in the country. But this company purchased this warehouse. They provide meats and foods to grocery stores and things like that. And they purchased this cold storage warehouse and converted it to freezer storage. And it's in Delanco, New Jersey. It's a huge building, 250,000 square feet. So in converting it from cold storage to freezer storage, they had to do a couple of things at least. They upgraded the HVAC, the refrigeration system, obviously. And they also had to add insulation to the roof. And if you look here on the left, this is in process. This is an old photograph. But on the left, you see polyiso cyanurate insulation, which is flame retardant. And on the right, you see what they were adding to the roof, which is 7 inches of expanded polystyrene, which is not flame retardant. As a matter of fact, it burns pretty well. And then after they started operating the warehouse as a freezer storage space, they realized their energy consumption was pretty large, and they decided to add solar panels to the roof to defray their energy costs. And so they did. They added 7,300 solar panels approximately to the roof, and you see them here. I mean, that's a lot of solar panels on the roof. And there were 3 inverters, and the system, the aggregate system, produced about 1.5 megawatts. Each inverter produced about, or delivered about 0.5 megawatt to the grid. They operated the system like this for about a year, and then this happened. This was a big fire. This was a huge fire. And you can see here, this is a photograph from a helicopter, a news helicopter, where they were watching the firefighting occurring. And what was happening basically is they just simply rounded the trucks around the building and poured water onto the fire, but they didn't put anybody up on the roof. And the reason they didn't do that is because they of fear of electrical activity on the roof and concerned that there could be a risk to the firefighters. So they basically poured water on the fire. It was the XPS insulation that was burning because it was the roof that was burning. And the outcome was this: it was a total loss. The value of the loss was estimated in the range of 150 to $200 million. So it's a big loss. And so because of this, there were a lot of stakeholders, a lot of insurance companies are involved, and people were brought in to basically assess what happened. And we were brought in to do that task. When I say we, I work on, when I do projects like this, I work in a consortium with of people. And we kind of assemble a team together with the needed competencies. And in this case, we needed people who were experts in firefighting, cause and origin analysis, solar industry custom and practice, scene reconstruction, that's pretty important, electrical engineering, mechanical engineering, systems people, and fire dynamics and computer modeling. And the investigation is conducted using the practices that I've defined in NFPA 921. So basically, the fire origin was determined to be in the vicinity of a refrigeration air handling unit, a solar panel string, obviously, because the roof consists of solar panel strings everywhere you look, and multiple other devices. So what was the cause? That's what we were there for, to figure out what was the cause. And these are specs for the solar system. And we don't need to get into specifics, other than the fact that, excuse me, there were 7,300 panels, that each panel produced about 235 watts. There were 13 panels per string. So basically the panels are concatenated together in series, and there is approximately 7.8 amps of current flowing through each string. These strings, 7 strings are merged together in a combiner box, and there were 27 combiner boxes per inverter. And if you do the math, that all works out. But of note here is the fact that there's almost 8 amps flowing through an individual string, which is a lot of current. That's a lot of that's DC current. And the one thing you don't want is a ground fault in that situation. So other things to consider. There are miles and miles of wiring up there. Hurricane Sandy occurred sometime between when the solar panels were installed and when the fire occurred. There were 1,200 hand crimp connections that were made on the roof by somebody with a hand crimp tool and a wire spool. There were mismatched connector types. The installation and custom and practice needed to be evaluated, which we'll look at here momentarily. And what was the what was the maintenance and oversight of the system during the period that they actually ran the system? So here you see a picture of a combiner box, and you see 7 of the module strings coming into the combiner box. Each one of those wires that you see there, and we'll look at that a little. Here's another one. This is a different combiner box, but it's the same thing. 7 wires are bringing approximately 8 amps, 7 to 8 amps of current into this combiner box. The code requires that be all of those wires should be a conduit, but they were not. And there, obviously, we just saw 2 that were like this. And there are a number of combiner boxes there are like 81 combiner boxes on the roof. So it's likely there are others that were in this same condition. And then if you look inside the combiner box, and then this is one combiner box again, this is after the fact that was recovered from the site. And you can see 7 strings, 7 wires coming in representing each string. And you see the current return connection, and you see corrosion all over the place. You also see corrosion on the ground connection. And you see this is a PVC plate, and underneath there's evidence of water. So this is not good for something that's carrying as much power as being run through this combiner box, and 7.8 amps for each one of these wires. So there's a point of concern. And the other thing I should point out here is that there are watertight connections here, but trying to seal a group of wires like this in a single watertight connection is not good practice. Secondly, excuse me, the custom and practice in the industry for how you actually route wires. The wires you see here are wires that come with the solar panel. And the way the solar panels are built, you just snap these together. These connectors are called MC connectors, and they just snap together and put the panels in series. But at the beginning of that series of connections and at the end of that series connections, there are field wiring connections that have to be made. And what was found is that the field connections that were made not with MC connectors, which is a brand, but with Amphenol connectors. And apparently, they're not compatible with each other. And that creates the risk of a bad connection. They look compatible with each other. They actually snap together. But there have been instances of much smaller fires, but documented incidences that have occurred as a result of connector mismatches. In addition, as you can see, the wires are festooned, laying right on top of these pavers that are holding the solar panels down. So that presents the possibility of abrasion of the installation. And this is but one photograph of the as-built installation. There are others. So this brings up the question of the connectors. And so we started looking through the evidence. There were boxes of evidence that were stored in a warehouse down in the Philadelphia area. And here's in the upper right-hand corner, you see a connector back shell that's cross-threaded. So this connector here would not have been watertight. And this connector down here has evidence of corrosion. And corrosion in an electrical connection results in high resistance or increased resistance. If you have 8 amps going through a corroded connector and its resistance is increasing, you get more power as the resistance goes up, as the corrosion. So basically, you end up with high resistance, which produces high power. That high power creates high temperature. High temperature creates increased resistance, and you end up in a thermal runaway condition potentially. So with increasing resistance comes increasing temperature, which causes increasing resistance. I think you get the point there. And on the right, lower right, is a connector that was not fully assembled. In other words, the contact was not pushed all the way into the body. And so consequently, the contacts did not fully engage with each other. But that isn't evidence that this caused the fire either. So we're looking for something to corroborate this with. And so the next step was to look at the inverter. The inverter is approximately the size of 2 refrigerators. And the inverter tracks current and voltage and power production, I think like every minute. And there's a small SD card in the device, and it writes to a file and It records all that data in an Excel readable format, turns out. So there's, as I said, 3 inverters. And inverter 16 is the inverter that is essentially surrounds the area where the fire actually started, the origin of the fire. So what we decided to look for is, what are the characteristics of these 3 inverters? How are they performing? And is there anything novel or unique about inverter 16 that might indicate that there's something going on the roof? So this is a result of the analysis of that Excel data. And what you see here is in July of 2012, you see a ground fault error that occurred, 3502 ground fault error on that inverter. Well, that particular error and that is, by the way, that is inverter 16. Now that's the year before the fire. A 3502 fault can only be cleared by somebody going into the electrical cabinet of the inverter, unlocking the door manually, flipping the breaker because it's trapped, that error is trapped or identified by a 5-amp breaker, resetting that breaker, closing the door, and restarting the inverter. That happened because that error was cleared and the system was put back into operation. But there's no evidence, there's no documentation of anybody going up on the roof, or even about any documentation as to what they saw in the inverter. But we do know this inverter was put back into operation, except that it didn't produce any power for almost a month's period of time. And the owner of the facility never noticed that there was no power being produced. The other thing that was noticed in the data is that every single one of these days resulted in maximizing the number of anomalous conditions reporting. In other, the inverter was recording errors. It didn't document what those errors was, but it saturated the number up to, I think the maximum was 256 errors. So it saturated that error count every single day during this period. And then in August, there was another ground fault that occurred, and another 3502 ground fault. And they called the service company, the installer. And the installer came out and they realized, there's a problem on the roof. So they actually went up on the roof to find out why there was a ground fault. What was the cause? Now, again, there's over 2,000 panels in one inverter that is working with one inverter. There's a lot of connections involved there. And every one of those needed to have been evaluated. But it doesn't look like that happened. It looks like they found one connection that had somehow gotten trapped under a brick, between a brick and a piece of metal, and ground faulted. They fixed that and restarted the inverter and left. And what you see here is, yeah, the system started up again, but it didn't produce any power. And then a number of days later, the display on the inverter had to be changed out. So the same company came out and changed the display. And again, found some other problem. This is where we lose all information. When they installed the new display, they set the date to be sometime in the future. And the minute they did that, they caused the inverter to start overwriting its history. So that's when data recording was stopped, or at least we had no access to it. But we were able to send the SD card out to a company to recover data that had just been erased. So we did get 4 days of data on the day of just prior to the date of the incident. The incident occurred in 2013. It's approximately a year after what you see here on the screen. And lo and behold, what you see here on the screen is relatively close to what happened just before the incident. There was a 3502 fault that happened approximately 2 or 3 hours before the fire started. So the fire must have been percolating up there for a period of time. And then shortly after that, excuse me, inverter, I'm gonna have a drink of water here. Shortly after that, the inverters 15 and 17 was shut down. again, for faults that they experienced as a result of the fire. So our conclusion from that is that we can't really say this is exactly what happened because we don't actually have the evidence because it got destroyed in the fire. But there's a lot of circumstantial evidence indicating that there were observable operating problems on the roof, that prior repairs that were made to try to get the inverter up and running again were not sufficiently thorough to identify all the anomalies. There were missing ground wires. I didn't point that out earlier. I should also mention that some ground faults are not detectable. Number one, it depends. Depends where they are. If they're upstream of the combiner boxes, sometimes you can't detect those. But also the ground fault has to be in excess of 5 amps because the detection breaker is 5 amps. So if you have 4 amps, the inverter is just going to continue operating. There were mismatched connectors and there were corroded connectors. And also when they were building up these connectors on the roof, 1,200 connectors, they basically handed somebody a crimp tool and a spool of wire and said, go make them. They didn't implement a quality assurance program for what is essentially a manufacturing process. And the mere fact that we were able to identify defects in connectors from the small number that we had that were recovered at the site, statistically indicates that there's a high probability there are many other connectors that had the same problem or similar problems. So that's what happened with that solar fire, which to date is probably the largest solar fire to have ever occurred in the United States. But solar is great. I've got 24 solar panels on my roof. One of the things that changed is that the codes changed as a result of this. And there was the advent of microinverters and string inverters. And so if you look on the panels that I have on my roof, there is an inverter for each panel. And so therefore the system would trap any sort of ground faults that would occur right at the panel and not have it turn into some huge gigantic problem. So I think this is not a statement that solar is a problem. Solar can produce problems, but properly designed and properly done, solar is great. Now on to a residential natural gas explosion. So the building here is a duplex house in Lawrence, Mass. You can see, obviously, it's the building, it's the unit on the side, on the right-hand side. And what you see here is the building prior to the incident. And the 2 lines in the street are gas mains. The red line is a 108-year-old cast iron 6-inch gas main. And the green line is a 12-inch high-pressure gas main that was installed a few years before the incident. It turns out that the building that caught fire was connected to the 12-inch main and not to the cast iron main. So, but yet the cast iron main fractured right at the point of this red X here, which is 60 feet away from the building. So our task was not so much to evaluate why it fractured, but how is it possible that the fracture could have resulted in the explosion in that building that wasn't even connected to that line. So here's the 108-year-old gas line. You can see that the fracture location is identified. There's already been a repair that's been made. And you can see there are a bunch of big rocks and stuff in the street. But that having been said, that's not what we were there to worry about. We were there to worry about the plume and how it got to the building. So again, I should say, by the way, that from the fracture, as I said, to the building, it's 60 feet. So how did that happen? In order to figure this out, we had to pull together a team once again, and that consisted of, again, cause and origin people, civil engineers, mechanical engineers, again, a scene reconstruction person, and fire protection engineering people. And so this is a graphical rendition of the building created by that reconstruction person who's really does a great job. And here what you see is the basement of the building and the first floor. What we found was that it's a hot air system where the furnace is taking air from the return air duct, heating it and returning it back to the floors up above. And just prior to the incident, Lawrence, Mass experienced like a week of 0-degree weather. So things got really cold. And so the furnaces were running full time during that period of time. And what you also see here is a crack. There's a crack in the foundation right here. And obviously we've got these arrows indicating, yeah, maybe there's some gas coming through here. We don't know. So the grill in the floor was the only means by which air could get back down to the furnace down in the basement for recirculation. Yet a quick analysis of that grill indicated that it's approximately 3 times, a factor of 3 too small for the amount of air that needed to be returned. That combined with the fact that the return air duct in the basement was actually open on both ends. It should have been sealed off. The building code requires the ductwork to be fully closed. It wasn't. And so we had a situation where the return air was going through the return grill, which was a factor of 3 too small, causing a pressure drop. We knew what the flow rate was because we knew the specs of the furnace. And so we knew what the pressure drop was, and that was determined to be about 0.16 inches of water column to the negative. So basically we were creating a vacuum in the basement because the furnace was sucking air from the basement. So we decided that we would use a computational tool called computational fluid dynamics, or CFD, to evaluate gas migration in the street to the foundation. And that also required us to determine what was going on at the crack. So we built this apparatus. These 2 young gentlemen here and that old gentleman over there on the right was just watching to see what was going on. But we pulled a vacuum equivalent to what we had calculated actually existed in the basement and measured flow rates at various vacuum levels and plotted it and used that as input into the CFD analysis of the soil, gas migration through the soil. And here's the result. So what you see here is, let me first explain what you're seeing here. This is a cross section through the soil, looking at the foundation and looking at the pipe. So it's like we cut the pipe and we're looking through the end of the pipe over here in the street. This red and blue area represents the soil. The gray is the frozen top layer on top of the soil. This is the street, and also the grass over the lawn before the house. And this yellowish area is the building itself, the foundation of the building. And here's about a 1-foot area where freezing did not take place, right? Because there's heat going out the foundation through conduction, and that prevents the ground from sealing. So this is the model. And we first modeled a compliance system. We had basically the undersized grill, and we had the foundation with closed, with not the foundation, but the return air ductwork sealed off as it should have been done if it had been done through code. And what we determined was the gas concentration at the foundation was really high. It got pretty high. But the amount of gas that migrated through the crack was only about 1/4 of a cubic foot per hour, not much. And that's because the pressure differential between the inside and the outside was essentially near 0. And so the only thing pushing gas through the crack was diffusion. But when you remove the openings and put it and basically create the negative 0.16 inches of water pressure in the basement, a whole different picture emerges. All of a sudden, you see the gas plume getting sucked into the crack, and you can calculate that the gas flow rate into the building jumps up by like a factor of 1,000 to around 200, almost 240 cubic feet per hour. That's not good. Now we have a lot of gas going into the basement. And here's the result in the building. One of the guys actually created an Excel model of gas flow through the building to calculate, well, how did this manifest as gas concentration in the building itself? What was the gas concentration? And the reason for that is because it's important to know the gas concentration, because the susceptibility to ignition is related to the concentration of natural gas. And the LEL, which is the lower explosion limit for natural gas, is 5%. So if the natural gas in the concentration gets to be greater than 5%, it's explosive. If it's less than 5%, it won't explode. So what you see is, with a non-compliant open air duct in the basement, at time 8.5 hours, the concentration in the kitchen gets above the LEL. And so what happened in this case is, and I should mention that there were injuries, but nobody passed away in this incident. But this woman smelled the gas, got up to see what was going on, turned the light switch on in the bathroom, couldn't see anything. But when she turned the light switch off, boom, the incident occurred. And she ended up on the porch, and she was injured, but she was, she survived. The gas concentration in the basement got to be even higher than the concentration in the kitchen. But importantly, if the ductwork is sealed on both ends, according to code, even with the undersized grill, the gas concentration in either the kitchen or the basement never gets up anywhere near the LEL. So the conclusion from that is that we found gas concentrations at the foundation in either case got to be as high as 86%, which is very high. And that the foundation crack formed the pathway for gas to flow into the basement. But the undersized floor grill combined with the open air duct created negative pressure in the basement. The gas concentration in the kitchen exceeded 5% LEL. And a code compliant installation, in spite of those issues, would not have exceeded the LEL, and the incident wouldn't have occurred. So, in summary, codes exist for a reason. It's important to follow codes. Cause determinations are not absolute, because there's uncertainty in all of this stuff. Typically, in large fires, the actual evidence that you really need to make a determination as to what happened gets completely destroyed to the point where it's not really usable. The third issue is, or learning, I'd say, would be that complex investigations really require multidisciplinary teams. And we're really fortunate in that I work with a group of people located, a couple of guys in California, guy at NC State, some people in Massachusetts, and we have a really great group of people that bring all of the skill sets that are necessary to do a really good job here. And that scene reconstruction is critical, because typically there's nothing left to be seen after the incident occurs. And so that's it. That's the extent of my talk, and happy to take whatever questions there are. Marty, it's all yours.
Thank you, Don. That was really great. So yeah, pop those slides down, and really interesting presentation. So one of the ways that I try to get a little engagement is my little trick is the smiling screenshot. So if you're within range of my voice and don't mind turning your camera on for a second and will give me a little smile, I'll grab it in a screenshot, and I'll add it to the E2 Tech archives. And I realize that not everybody wants to do that, but that's nice if you can do it. And then we'll go right to questions. And if you can either put them in the chat, or you can ask, or just pop right up and ask directly, which is preferable. I think it's good. It creates a little bit of engagement. Okay, what a crew. All right, on three, a nice big smile. 1, 2, 3. Gotcha. All right. Who's Who's thinking of a question? What does this bring to mind for you? I have several, but it's better if someone else has some questions.
Yes, Don, I'll start. Dave Norman. How common do you think the connectivity issues are on solar installations, and how good are companies nowadays at having quality control methods for those connections?
Great question, Dave. Thank you. There are, first of all, there industry, there's a solar industry group that has defined practices in the solar industry. And there are training certifications. There's all sorts of things that have been done in order to resolve and prevent things like this from happening. The National Electrical Code has been updated to largely fix many of these problems. Some of these issues were really not known back when this occurred. So this incident actually resulted in changes to the code. And also it created this push towards making inverters smaller and smaller and smaller so that they could capture the, instead of capturing a ground fault that's 5 amps or greater, you can capture a ground fault at a much lower value. I mean, ground faults can still occur, but you can catch them well before they're a problem.
Great question. Shall I just sit? Go ahead.
Yeah, Eric Sonics and Haraldson Blair. We're working with a company that makes service equipment for the natural gas industry. And the details of that are important to this. And we've been looking at a specific safety issue in the design of a new product. And we're not experts in safety. We're just engineers who can look at something and say, huh, well, that looks like a bad idea. Let's figure it out. But is there a group or groups, including yours, who could be helpful in preventing these kinds of accidents, not in the street, but in the particular piece of equipment of interest? You got to look at the whole thing. You got to think about ways that it could fail. And then you got to think about consequences of that kind of failure. And it intrigues me that in this case, the potential failure follows on a failure that occurred in California, where the problem was, excuse me just a minute, the problem was poor quality control of some pipe connections, tubing connections, actually. Nobody ever gauged the connection, and a large hydrogen transport truck burned to the ground and did a lot of damage just because of a failure of quality control. So that's just one example of a manufacturing problem that also came as part of a design problem. They didn't design in a quality control step. So who should we talk to?
Well, without a doubt, by the way, there are a couple of people. There's one gentleman in particular that I can think of that actually would be great to talk to. I mean, he knows that side of the business inside and out. There are a couple of people like that. But in general, I think that what you're doing is really important. If you think about what happened with Columbia Gas after this incident, where they were doing excavation in the street, upgrading their 110-year-old pipes, and they made just a procedural error, right? The pressure sense lines, they moved the pressure sense lines, or they didn't move the pressure sense lines when they turned on the gas, and the system thought there wasn't any pressure in the line. It kept ramping up the pressure. Yeah. And they ended up damaging hundreds of homes. And I'm sure everybody heard about this problem in Lawrence. So yeah, errors occur. Yeah, errors occur for sure.
I think that's, I mean, this is ideal. Thanks for asking that, Eric. And I'll make an email connection. This, two of you may be already connected, but this is our goal, right? So if there's an opportunity to prevent something in the future with this discussion and expertise that the two of you can collaborate on, so that's good. I want to hear more about that. I'm tempted to ask about the current LNG situation in Freeport, Texas and so forth, but I want to let other people jump in and ask questions. It looks like John Furland has a question.
Don, I had a couple of questions related to process, and I noticed in each investigation there was some overlap in the multidisciplinary team, but there was also some differences in credentialed people. Can you talk about how you begin to assemble the right team? And then the other is, a couple of your slides reference the NFPA 921 fire investigation procedures. And could you explain what those are and the relevancy of or the importance of following them in your work?
Yeah, sure, John. It turns out actually NFPA 921 in some circles is a little, what's the word I'm looking for here, controversial. But nonetheless, though, it defines using the scientific method to root out all extraneous causes before you really decide what the fundamental problem is. And what that does is it tends to slow down investigations as you run things to ground. For example, was there a oily rag on the roof that might have spontaneously combusted? And I say that because I did get involved in an FAA fire even years before this one, where that's exactly what happened. They were installing a new roof on an FAA building in New Jersey, and in Delaware actually, and there's a lot of solvents and things that are used in installing the roof, and somebody threw a rag, in the trash, but the trash didn't get emptied at the end of the day, and so they were spontaneously combusted, and there was a big fire on the roof. So that is an example where it was an oily rag. But in this case, we ruled that out because there was no permitted access to the roof. The roof was locked. There had been an inspection of the roof after everything was installed. All trash had been removed. So it was a really unlikely possible cause, but we had to run it to ground. And we had to have a reason for eliminating it. And that's what we did. So basically NFPA is pretty all encompassing, but in essence, it just defines the process by which you go about, zeroing in on the final, what is the most likely cause of the fire. I should mention also.
Yeah.
Yeah. Oh, I'll get to that. So one last thing about that point is you'll notice that there are cause and origin experts, and that's really kind of separated. Typically, the way it works is that there are people who are experts in origin identification. A lot of those folks are firefighters, for example, who have been trained in looking at fire patterns and being able to figure out, well, given what I see with this fire pattern, we think it probably happened right around here. And they're good at identifying, looking at the evidence and figuring out where it really started. The cause people are the engineering people. Once the origin has been identified, the cause people come in, try to figure out, okay, well, how did this happen and why? But to your point, also your question about the makeup of the team, early on, we just we kind of come up with, to be fair, try to put some parameters around it, what we think might be involved and who are we going to need to figure out what most likely happened. And in the case of the fire on the roof, we figured that we really needed to look at fire propagation on the roof. So there's one of our guys he's at UC Berkeley. He's an expert in fire modeling. He participated in the group. He was a great asset. in terms of modeling what happened on the roof from a fire initiation perspective. We knew we needed electrical engineers because we knew could very well be a solar problem. We didn't need any gas analysis people because there was no gas on the roof. So I think you get the idea. You kind of look at the phenomena that are involved and you find people that are experts with those particular phenomena. That's how we do it.
Excellent. Eli.
Yeah, so referencing the solar roof fire, there's a lot of focus, obviously, it looks like, in analysis of installation practices, and kind of back in that day, as I suspect a lot of us know, there's some pretty shady stuff going on and a lot of QA/QC stuff going on. I didn't really hear you mention anything about the design. One of the good ways to kind of mitigate problems like this is to be very clear about what is and isn't good installation practice in the design, including ground fault analysis. That's kind of a normal part of a PV design. Did you see any, flaws or things that were overlooked in the design itself, or was it really just kind of likely started by crappy installation connectors and whatever else? You know what I mean?
Yeah, that's a great question. Thanks. So at the time, this may still be true. One of the things I'm not, by the way, is a solar expert. I was brought in because I'm a mechanical engineer and I have some systems knowledge. But what I did learn is that these inverters are common inverters. The 500 kilowatt inverters, they were common inverters at the time. And to the degree that we could assess what went on, the design was okay. The design seemed to be consistent with industry practice from what we could see. As I think I mentioned, there was a custom and practice person that worked with us on that. But the issue was that basically the wires were not tucked up where they needed to be. It's that kind of thing, that there were issues with attention to detail that I think that probably anybody on this call would have probably picked up on pretty quickly.
Got it. Thank you.
So the point, I think, is well made too. I mean, and I think, Dawn, you and I kind of commiserated about this and prepping for this. It's a sort of a series of unfortunate events, and no one should infer that there's inherent dangers in solar install any more than any other. As a former roofing guy, I'm very interested in the FM or not FM rated roofing assembly, and all these things seem to have kind of come together in an unfortunate way, and practices have evolved, and there's been some learnings, it sounds like. Who's ready to kind of close us out with a really killer, encompassing question? Maybe Peter, I'd pick on you, or anybody?
I've got a quickie.
All right.
Where was the code inspector in all of this? There's somebody who approved the installation. Are there government-based code inspections of solar installation?
Yeah. So Eric, I think the term that applies here is the authority having jurisdiction, right? The AHJ.
Yeah.
In this case, is the code enforcement person for the town. And the town was, I guess you could say, probably not really well prepared for this. This happened a number of years ago. Large installations like this were not common, and code enforcement was done. The fire chief was involved, but I don't think anybody was really, I guess you could say, fully qualified and up to speed to really inspect this as it should have been.
Yeah.
That's a learning, right? And there's, I think the other thing you mentioned too was the fire department, wasn't comfortable getting onto the roof, and that might be something that would be, with training, addressed differently too, right?
Yeah, exactly. As a matter of fact, the firefighter expert that we did have with us, he's also an electrical engineer, and he was describing to us about how they actually have special nozzles that you can use in the presence of high potentials to prevent basically back arcing, I guess is the concern. And so there are tools that firefighters have to deal with electrical fires, and but you have to be trained with them. And I used to live in New Jersey. One of the things I remember about New Jersey, which was a surprise to me, was that every single town had volunteer fire departments. You know, when this was this was an installation installed in a relatively small town. And I think the fire department was probably, I don't remember 100%, but I think they were volunteer. So training is potentially an issue here. You're right.
Yeah, an opportunity.
Yeah.
Well, Don, well, thank you. An excellent discussion. Wonderfully done. Yeah, round of applause. And we
you.
have recorded this event. We will get you the slides, and I hope that you'll secure the services of Parent Technology Group if you have a need or want to make a connection. I will make sure Eric and Don are talking about that potential project. And please do register for this. This one is a very interesting talk that will make some good comparisons between California and Maine, offshore, wind installation, depths of water, you name it, with some experts from Burns and Mac. So I will just wrap it up there on this beautiful Maine summer day. And I know many of us have 1 p.m. meetings. Thank you again for your support of E2 Tech. Thank you again, Don, and enjoy a beautiful and safe afternoon. Take care.
Thank you.